Welcome to lecture number 7 of module 2. In previous lecture, we have seen that equal area criteria can be used to analyze the stability of the system, and that is only applicable for this single machine infinite bus system or two machine system. And the last example we saw that if you are increasing the sudden increase in the power, how your system will be reacting and what will be the stability of the system. Now let us determine what will be the maximum power that can be increased on any machine over and over what is loading, present loading, and that is basically governed by the stability of the system. Let us take your machine is loaded. Again, this machine, now here I will draw, this is your synchronous machine. It is here its reactance, and this is the transformer, and then we have two lines, and then it is connected with the infinite bus here, that is your infinite here. So this is your voltage angle 0, that is V infinite. Here it is EF angle delta. So in this case, here your PM, that is your mechanical power that is entering, and now I can say this is a PM naught. For this case, your PM naught here, where your machine is operating at angle delta naught, and this is your PM, means A point will be the operation when your feeding power, this mechanical power, is PM naught. As again I explained that the operation point will be the intersection of this mechanical power characteristic, that is a PM line here, and then it is your PE line, this is your PE curve, which is a function of sine delta. So the intersection here point A. Now the question, I want to know how much power that we can increase, that is your PM we want to calculate, so that our machine should be unstable without losing synchronous. To know this, we have seen that equal area criteria is used to determine the maximum additional PM which can be applied for stability to be maintained. With the sudden change in power input, the stability is maintained only if the area A2, this area, this is your A2, at least equal to area A1. Means this area here, it will means at least equal. Means this area may be larger, but it should not be less. If this area is less than this A1, then your system is not stable. So we want that maximum power that we can inject, suddenly we can change on the loaded power system or on this generator, that can be determined. That means area A1 will be equal to area A2, and then we can determine what will be the PM value. To determine this PM, we have to calculate this delta 1, or we can calculate this delta max, because this delta max is nothing but here delta max will be, or you can say is a pi minus delta max will be your delta 1. So to determine delta 1, we want to know the delta 1, then we can get the point B, because the P characteristic we know. If we put this delta value in that one here, delta 1 in that P characteristic, we will get the point B, and thus we can determine the PM. You will see in the following lines. So here, now this area 1 here is oscillating power, means this area, as I said, so to maintain the stability, area A2 at least equal to area 1 can be located above the PM if area A2 is less than area 2. If this is less than area 2, the oscillating momentum can never be overcome. The limit of the stability occurs when the delta max is at the intersection of the line PM here, means this PM we want to determine, and the intersection of P and this PM will give you delta max, and this will be always here, it will be delta will be more than 90 degree this side, means here in this zone, here it is your pi by 2, that is 90 degree. Applying the equal area criteria to above figure, we can have this area A1, this area that is ACB, here you can say area ACB, or you can say area 1 will be nothing but integration from delta naught to delta 1 PM minus this PE curve. So means this is nothing but here it is integration of delta naught to delta 1, here this PM minus PE d delta. So this PM is a constant, so integration of this we can take the PM outside, so it is a delta 1 minus delta 2, the first term, and another term this PE with the minus sign we are integrating from delta naught to delta 1, that is a P max sin delta d delta. Similarly this area 2, it will be the integration here from delta 1 to delta max, and now it is a PE minus PM, because this curve is over, and then this minus this integration from here to here will be your area 2, and then we can know this PE is a function of sin delta, so it is integration from delta 1 to delta max P max sin delta d delta minus this PM is a constant, so delta max minus delta E delta 1. So based on the equal area criteria, to the system stable, at least the area A2 should be equal to area A1. So this area 1 for maximum PM, the area A1 should be equal to area A2, and then from the previous equation if we equate we will get this expression. Now here the PM we are getting here, and that PM is nothing but again we can get the PM is equal to P max sin delta max, means this value the PM will be again that will be your P max sin delta max, we can get this point, and then you can substitute this, so we will get a expression of a delta max value, and this is a nonlinear equation, means we have the sin delta max, we have another delta max here, we have cosine of delta max, and of course the cos delta naught is known to you. Delta naught is your original where your machine was operating, and that can be calculated because PM is known to you, PM not here. So this equation is a nonlinear algebraic equation and can be solved by any iterative techniques, including your Newton-Raphson method, Gauss-Seidel methods, Gauss-iteration methods, so on and so forth, so that we can determine delta max. Once this delta max, means here our intention is to find delta max. Once you can determine the delta max, then the maximum power P max will be your P max sin delta here, this PM, or you can get this one directly. So you can even though where delta 1 is your pi minus delta max, or here you can simply write this P max sin delta max. So this will be the maximum power that you can load above this PM naught without losing the stability. So this is one way to determine that how much you can load suddenly. Again question here, if you are continuously increasing, then your maximum loading here is up to P max. But the sudden increase here, for the sudden means it will be accelerating and deaccelerating, because here is the acceleration power, here machine is a deaccelerating, here the 0, and here again is accelerating, and so on and so forth. So since why this area A1 is called the accelerating, because the PM is more than PE, so what will happen? Your machine will accelerate and it will store the kinetic energy. However, this area A2 is the deaccelerating area, because your PE is more, means the power, electrical power that you are taking from the system is more, means here, and than your power that you are feeding to the turbine. So this is a deaccelerating. So accelerating power must be equal to your decelerating power. Then the PM can be determined. Now let us see another consideration, means how this equal area criteria can be useful for determining other stability criteria. Let's suppose there is some fault. So if we'll consider the three-phase fault, the three-phase fault can be a bus fault, it can be in the line fault, and it can be anywhere in the line, either in sending end or receiving end or in between line. So let us first consider the three-phase fault at the generator terminal here, that is this terminal we are putting. Basically this is a generator, this is a GT, generating transformer, and this is a terminal where that is you can say this is a bus 1. So again this system is similar to our previous system, that here a generator is connected to infinite bus bar through two parallel lines, line 1 and line 2. Assume that the input power again here is PM is your constant, and the machine is operating steadily, delivering power to the system with an angle delta naught. Here means your delta naught is EF, means if you are here, I can say E angle delta naught during the steady state, and that will be shown in the next curve. A temporary three-phase fault, that is a voltage fault. Voltage fault means the fault without any up fault resistance, means directly three-phase to ground fault, occurs at the sending end of one of the transmission line at the bus 1. Here three-phase fault, let's suppose, has occurred in line 2. When the fault is at the sending end of the line, no power is transmitted to the infinite bus. If the bus fault is here, what will happen? There will be no power which will be flowing to infinite bus. So your PE at that case, it will be your 0. Since the resistances are neglected of the line, the electrical power PE is 0 and the power angle curve corresponding to the horizontal axis. Means you can see what will happen. This PM here, A was your operating point, because your PE here is equal to your PM naught, that is the PM naught that you are getting. So suddenly there is a fault. So what is happening? Your PE becomes 0. So this is suddenly coming to this point, and then till the fault is persisting, here it is going, and at the delta 1, once fault is cleared, and then again it is going back to the PE. Again the PE is going to be delivered to the infinite bus. So in this case, the machine oscillates with the total input power as the oscillating power, means the total PM, because we are not taking PE from that generator, so this machine will get oscillated, means your input power is more than output power. So the whatever the power you are feeding, as you know the energy conservation law, then this energy will be stored in terms of kinetic energy, and if the kinetic energy of any system is increasing, means the speed of that machine rotating mass is increasing. So thereby the increasing its speed, storing added kinetic energy and increasing the delta. If machine is oscillating, what is happening? Now delta will be changing. The delta is angle. If you will see what is now question is delta. Delta is, let's suppose this is your reference angle, any arbitrary reference angle. Here this is your delta naught, and your machine here, this is a rotating two fluxes here. This is your synchronously rotating here, and it is actual rotor speed omega r. This is omega naught. So this difference, that angle it is, that means your delta is your omega r minus omega naught, that is a T with a delta naught. So if your machine is accelerating, this is increasing, this is your synchronous speed. So what will happen? This term is increasing with the time. So your delta is increasing. Here delta naught is any reference, it may be this, so delta naught will be 0. So once your machine is oscillating, means your delta is oscillating, increasing, and once it is a decelerating, means your delta, that is the angle delta I have defined with this one, it is a decreasing. So that is written here, the increasing angle delta. When the fault is cleared, and it is assumed that the fault was temporary, and the fault is cleared without the tripping of the line, because it was the bus fault and bus fault is cleared. So both lines are assumed to be intact, means your impedance of the system is not going to be changed. So again it will follow the same PE characteristic. The fault is cleared at delta 1, which shifts the operation to the original power angle curve at point E. Here this is your point E, means your fault is cleared here, means it will suddenly follow this delta curve, because this is a PE, here PE is 0. So this PE it was running at this point, suddenly due to the fault the PE becomes 0, this is your 0 PE, this is a PE axis, and once fault is cleared, then it will again, it will follow the PE curve, that is here it is your PE curve, that is a function of sine delta. So it is coming to your E point. The net power is now decelerating, and the previously stored kinetic energy will be reduced to 0 at point F. when the shaded area, this shown by area 2, equals to the area shaded in ABCD shown by this. Now you can see this area A1, as I said, this one is your oscillating power. Means where in this area A1 your machine is oscillating and is storing kinetic energy. Now once this kinetic energy is stored in the machine, what is happening at the E point? You can see this is now electrical power is more than your mechanical power. Means you are taking more power. So whatever the energy is stored in the machine, that will be taken out, and this area here, it is called your de-oscillating. Means here it was oscillating. Now from here it will de-oscillate till F, when again the oscillation will become 0. So again you can see the delta is keep on increasing here until it is delta max. Here again this your de-oscillating power is 0. Then again it will find that this is more than this. It will try to retard, and again it will coming back. So it is again there will be oscillation around point A, and finally due to the damping of the system it will be damped out, and your final steady state operation of the system, it will be a stable operation. Now the question again here arises, if this area is less than this area, if this area is more A1, means your A1 is greater than area 2, until what point? Till certain range here, then the machine will be unstable. So we can see the rotor angle would then oscillate back and forth around here, this knot, means here it will be oscillating at its natural frequency. Because of inherent damping in the system, the oscillation subside and the operating points return to the original power angle delta naught here, that is at point A. So by applying the equal area criteria, this area A1, that is integration from delta naught to delta 1, here that is the integration of here, it's completely PM minus this 0. So this is a PM delta, and area A2 will be delta 1, integration from delta 1 to delta max. Here this PE minus PM d delta, means oscillating area 1 will be equal to oscillating area 2. And now you can see how much you can move ahead. This is F. Let's suppose you have increased further, means it is not clear at this one. Let's suppose your machine fault is clear at this point. What will happen? Now this area here, it is up to this area, and once fault is clear, now it will follow here, and then it will go up to here area. Now area 2 will be this much completely, and it will be your area 2 is this much. So still your system is stable. Let's suppose further you have increased. Let's suppose you have your delta 1, your fault is cleared after longer time. So this area is now reached here, and now you have gone here, and again you can see the area this is bounded A2 is now less than your area A1. Complete this area. This area here is larger than this. So in this case your A1 is more than A2 and the system will be unstable. So what we normally do, we try to determine what should be the value of delta 1. Here what I am going to explain that how much this delta 1 that can be maximum value, means the fault can be cleared so that our system will be stable. Why we are very concerned about this? This delta 1 means that is a maximum delta 1 at which we can clear the fault, our system will be stable. This is known as a critical clearing time. Critical clearing angle, if you are calculating this delta, if you are calculating in the time, then it is called the critical clearing time, CCT, or here delta 1 is your critical clearing angle. In the next slide we'll see that's delta C is your critical clearing time. That's what will be this value. We want to determine this so that if your fault is cleared before that, so in that case suppose your fault is cleared here, so this condition will be always here, this area A2 will be always you can say more than your area A1, means your system will be stable. So from here, this complete area is always larger and then A1. So we can say our oscillating power will be always less than your de-oscillating power, so the system will be stable. To determine this critical clearing time, that is very, very important. The critical clearing angle is reached when any further increase in delta 1, that is a delta 1 here, causes the area A2 representing the de-oscillating energy to become less than the area representing the oscillating energy, that is your A1. This occurs when the delta max here or the point F is at the intersection of line PM. Here this is the line PM, this is line PM, and this is curve PE. Then it is the intersection point F as shown in this figure. Now for this critical value, here this point cannot come below because this is the de-oscillating. Up to this point PE is more than PM, so this is a de-oscillating. You cannot go beyond this, because if you are coming here, what will happen? Your PM will be more than PE, and again it will be oscillating. So your system will be unstable if it is moving beyond this point. So we have to, this area A2 should be less than this delta max, and then we have to determine this delta C so that we can know if your fault is cleared less than that angle, then we can say our system is stable. To be very critical, for getting the maximum value of delta at which it is cleared for the stable operation, this area A1 should be equal to the area A2 here. So area A1, that is your ABCD, will be equal to your area DEF, this is area 2. So this area here, for this case, it is a PM integration from delta naught to delta C is equal to your integration from delta C to delta max, here PE minus PM. So it is a PM max, here this is nothing but your PE minus PM delta D delta. So integrating both sides, you can say left hand side here, your PM delta C minus delta naught will be there. Your another side here, it is a PM cos delta C minus cos delta max minus PM delta max minus delta C. So here this you can say this delta C will be cancelled, and we are getting a one equation of delta C very easily, and that we can say cos delta will be this function, or we can say delta C will be cosine inverse PM upon P max, delta max minus delta naught plus cos delta max. And delta max can be determined again. Here we know this is a PM, is your P max, here sin delta max. So if you will solve this, knowing this PM as well as PS max, you will get the two values of delta max. Means here in the previous case, if you will write this equation, this PM will be equal to, this is a PM at this F point, it is your P max, here sin delta. If you will solve here, knowing this PM, knowing this, you will get the two values of delta. One you will get the delta 1, another you will get the delta max, and these value will be less than equal to 180 degree. So since we are talking about the up to the pi degree, so we will get the two values. So first one, the smaller value will be your delta naught here in this case, that is here, and this value delta max we can get the another value, that will be again the pi minus delta naught will be the delta max. Means here delta max will be nothing but your pi minus delta naught. You can see from here it is this angle will be equal to this angle. So now we can get this because we are knowing this delta max, we know this delta naught, and then PM P max we know, and then we can determine the critical clearing angle, and this is known CCA, and that is one of the measures for the system stability. Means if your fault is cleared before this angle, your system will be stable, and if it is cleared after this, your system will be unstable. In addition, it is possible to find the critical clearing time, because angle is very difficult to say what is the angle and also measure. So time is very important, means at what time your fault is clear, and that is called your critical clearing time, and that can be calculated again by using the swing equation. Your swing equation is nothing but your h upon pi f naught. Here the double differentiation of delta with respect to time, that will equal to your Pm minus Pe, and this Pe is nothing but your 0. Because here in this curve you can see this is your Pe is 0. So we want to integrate from here to here where the Pe is 0, or we can say this is a Pe, so it is, we can write the delta, we can differentiate this equation, we can solve this equation. Here we will get the pi f naught upon twice h Pm t square plus delta naught, because it is starting from delta naught. So delta naught is added, and then this is with respect to time, thus delta is increasing. So if delta is equal to now delta c, if you will put this value, so at that time your t will become Tc, means at delta is equal to delta c, your time will become your Tc. So the Tc will be nothing but here it is delta c minus delta naught, here twice h is multiplied divided by twice f Pm under root, it will be your Tc, and this is called your CCT, that is a critical clearing time. So this time can be also determined. Now let us see the effect of the pre-fault load. Means earlier your system was loaded at the Pm1. Now in this what we are going to see, let us your loading. In this case again your fault same system, there is a three-phase fault at the bus. Say its curve is similar to the previous one. So it was operating at the point 1, that is a angle at delta naught. The fault was cleared after the delta c, and this we got the A1 will equal to A2, and system is stable. Now we want to see if your machine was loaded more than that your Pm1 value. Let's suppose your value is Pm2, and that is your Pm2 is 1.5 times more. Means this is more, then what will happen? In this case also, this critical clearing time, let's suppose the same, fault is cleared for the same duration. So what happens, you can say here again at the point 2 it was delta naught, and again this delta naught is different than this delta naught. But this duration from 2 to 3 is the same here as well as here. So this Pm2 is 1.5 times more, just already I have written Pm2 is equal to 1.5 times of Pm1 here. Now you can see this now area A1, that this time is same. This area is increased by 1.5 times. Means this area was A1, now this area 1A prime, means A1 prime will be 1.5 times of A1, because this height is increased by 1.5 times, where this axis is same. So this area is increased, now you can see, and at the same time your area 2 is decreased, means here what is happening, this area is now shorter, smaller. So we can see this again, that the increasing the pre-fault load by 50%, the Pm2 increases the acceleration power 1.5 times, here it is increased by 1.5 times. So based on the swing curve equation during the fault, here integration of d delta upon dt square Pm upon m, then we can write this delta, this is delta naught Pm t square upon 2m, again it is written m in terms of angular momentum, and therefore here we can see this is this angle. The change in the power angle delta here, this delta also increases by a factor 1.5 times. Consequently, at each side of oscillating area, rectangle 1, 2, 3 has increased by 1.5 times. This is increased by 1.5 times. The oscillating area 1, 2, 3 of here, means this area is increased than this one, is now much larger than available de-oscillating area 4, 5, 8, means this area is much less compared to this area. So what happens, if your pre-fault load is more, your system is again critical clearing time is lesser. Means you must clear your fault well before here so that we can have area A1 better more than your area 2. Means we should have some margin. We'll see. Now question is, what is this area? Because if your A1 is equal to A2, your machine will here decelerating power is equal to your accelerating power, and finally your machine will oscillate around the point 1, and finally it will be stable. So area of 6, 7, 8 is called the margin, and that is known as stability margin. Stability margin of the system. So if this margin is larger, then we can say our system is more stable. So this gives you relative stability, means this margin is an indication of your stability of the system. In this case, you can say your stability margin, if this area is equal to this, stability margin is 0. Means in the case here at the certain critical clearing time, as I said here, in this critical clearing time, this area is equal to area 2, there is no margin here left out. So if your system is cleared after this angle, your system will become unstable. But if it is cleared here, then we will have some margin here, and we can say our system is stable. So let us say the three-phase fault in the different scenarios. So far just we have discussed the three-phase fault that is occurring at the bus 1, but let us it is a fault is occurring in the line and followed by the tripping of the line. So during the pre-fault, again your system is as the previous just we have considered for all the slides. Same here, your generator, generating transformer, 2 lines and connected to the infinite bus system. So during fault, what is happening? Now fault earlier it was at bus 1, now I am taking fault at line 2, and that is your three-phase fault. And this fault is cleared only after tripping of this line. So this is your post-fault scenario, means your line here is tripped, fault is cleared. Now what is happening? The system impedance here is a different, here due to the fault impedance is different, and now after tripping this impedance is here different. Now in this case, what will be your X? I am using this X here, it is your X D prime, that is of here generator, your XT of your transformer, and plus here XL1 parallel to XL2, if you remember this value which I was using in lecture number 6. So this is your X in this case. Now in this case what will be happening? Your X will be your XD prime plus your XT plus your XL1, only one line is there. So now you can see this impedance is lesser than this X1 because the parallel impedance of the two systems is always less than the impedance of its own. So here this value is now more compared to this. Now during the fault, again the impedance of system is reduced. Further reduced, it is less than this because this is a faulty and less power is flowing into the system. To understand this, now you can see the curves. We have now 3 curves. One is your pre-fault, another is your post-fault, and then another is during the fault. So let your this curve A, outer curve from 0 to pi, and that is denoted by your A, and it is called the pre-fault curve. Means where all the impedances are intact, where X is your XD prime plus XT plus the parallel impedance of the 2 lines. Since impedance is less in that case, so what is happening? This curve will be higher. Why? Again you remember this is your VE upon XD prime, means X prime, simply sin delta. If this value is small, then PE will be larger magnitude. So it is outer where it is followed. Now after the fault, one line is tripped. So what is happening? Your impedance is increased, and that, let's suppose your point here C curve, that is curve here, that is following this. As you can see this curve. During the fault, what is happening? Again there is a voltage fault. Impedance is again increased tremendously, and the power which is flowing inside the infinite bus is reduced. And let's suppose it is this one curve, there is a curve B, and where it is denoted at the during fault, and it is denoted at the PE2, that is a during, here post, and one is pre-fault. Now you can see your loading of the system was PM naught before the fault. Your operating point was A because it is the intersection of your pre-fault curve A and your PM naught curve, and this is your operating, that is a pre-fault operating point, and the angle, that is angle of this excitation voltage, your delta naught is this one. Now let us fault we have applied. Once fault has come, what will happen during the fault that which is occurring here, this is suddenly it is shifting to another curve because always it will follow the PE curve here. Now the PE curve, it is now during the fault we have this curve, that is a curve B, and it will be following this curve. Now what will happen, now in this case your PE which is fed to the infinite bus is reduced because here it is the PM is more and P is less, so machine will accelerate. Accelerate means here your delta will increase. Let's suppose at delta 1 your fault is cleared, and this fault clearing is associated with this tripping of the line, means suddenly we have to reach the post-fault condition, that is point E of this curve, that is the post-fault curve P. And then what will happen, this is your accelerating energy, this curve, then here it is going to deaccelerate till F, till the point when the A1 it will be equal to A2, and then again it will go back and then it will be again oscillating, and your final point of operation will be now here, it will be another, it is your K point will be your the final point because it will be oscillating around this point and your system will be stable if your damping is there and the system will subside. So this is the condition when it is the fault, means during fault curve, this is during fault, this is a post fault, this is a pre-fault. So this is written here in this, with the fault location away from the sending end, the equivalent transfer reactance between the bus bar is increased, lowering the power transfer capability, and the power angle curve is represented by the curve B during the fault because less power is fed. Finally, the curve C represents the post-fault power angle curve, assuming the faulted line is removed. When the three-phase fault occurs, the operating point shifts immediately to point B on curve B. Here this is coming here during the fault, and the excess of mechanical input power of this machine accelerates the rotor, thereby storing the kinetic energy, and the angle this is increased here up to this point. So this is your point of movement. Here it is going back, and then finally it will be attaining now. Later that it will come follow this one. It will come here and then go back. So in this curve you will see that this area again is here, I can say in this vertical hash line, this is basically your the margin that the system have, means your system is stable no doubt, and this area, if this area is larger, we can say our system is more stable. If this area is very small, then we can say our system is less stable. So what happens, there is a possibility that fault, even though if it is not cleared, then here delta 1 less than that or at delta, so this value will be keep on increasing. So there is a possibility, let's suppose your delta is increased here, so this machine will go up to oscillating here, and this complete area will be equal to, if area A2, then this angle against theta delta C is called as the critical clearing. Means the critical clearing angle is the angle that beyond that fault cleared, the system will be unstable, and if it is cleared before that angle, or you can say that time, then your system will be stable and there will be no margin, means that is a critical clearing time. So to calculate this, the critical clearing angle, means I want to calculate this delta C at which this area up to this point, means that is your PM line, this area A2 will be equal to your area A1, then we can say our system is marginally stable, means angle beyond this, if fault is cleared, your system is unstable. To know this critical clearing time, because we have to plan our system, means your protective device including your relays as well as circuit breaker that must clear the fault if any fault occurs before this angle, and we can also calculate the time. So this delta C is the deadline Less than that, fault must be removed, otherwise your system, this generator will be out of unstable. So this area A1 will be equal to your area A2, and then we can determine again your delta C as the previous example. Again this area is nothing but now PM minus PE, again the PE here are the during fault, that is PE2, means I can say this area A1 will be your integration from here delta naught to delta C, and this one is your PM minus PE2 d delta delta. So this is your area A1. Similarly, your area A2 will be your integration from delta C to delta max, and this is your P now curve, it is your C curve, that is a PE3 minus PM d delta. So if you are equating this and integrating, for this case you can say integrating this PM is a constant, so we will get this PM delta C minus delta naught, this term. Another term here is with the negative sign, integrating from delta naught to delta C of this PE2, and PE2 is your P2 max, PE2 max sin delta we are integrating here. Similarly, for the another area 2 we can write in this fashion. And again you can see this PM delta C here, PM delta C, it is this side, it is a plus plus, it will be cancelled out. So we can determine this delta C, that is a critical clearing angle, it is a cosine inverse this PM delta max minus delta naught plus PM3 max cos delta max minus P2 max cos delta naught divided by P3 max minus P2 max. So we can determine the critical clearing angle for the different case. Similarly, we can go for the different one. Let us see. In that case, this fault is cleared by the tripping of the line, but there may be the possibility that the circuit breaker, those are in the line, they may have some reclosing facility. Why we go for the reclosing? Because whenever there is some temporary fault occurs, there may be possibility that this circuit breaker is opening and fault is automatically cleared, and after the closing it was found that there is no fault. For example, let's suppose there is a flashover on the insulator. Due to the fogging, due to the moisture on the insulator, there may be possibility that line, due to the higher line voltage, there is a flashover on the line insulator and there will be a LG fault. So your circuit breaker will be clear. Simply that's it will be opening, and then it will try after few cycles, again depends upon the circuit breaker configuration and type and make, etc. So it will try to reclose to see whether fault is cleared or not. For example, let's suppose some word has come into the wires, all three wire. So there is a dead three-phase fault, three-phase short circuit. So once this any live animal or a birds that is on that phase here, once that will die, automatically that is again that all these three phases are operating in isolation. So the fault is automatically cleared after one shot. So the circuit breaker normally for the EHV transmission line, they will have some reclosing facility. So with that we can see the line reclosing as well. Means here our pre-fault system as usual in the previous case. During fault we have the three-phase fault. Now here the fault is cleared by the tripping, and again it is the line is reclosed with the help of the reclosing facility of the circuit breaker after few cycle, and now again your system configuration here is equal similar to your the pre-fault condition. So now what will be the scenario? To see this, again we have now three, you can see three categories. Here this is equal to this, means your pre-fault and your post-fault with the line reclosing is your same impedance, so same curve, and that curve is here, it is written that the PE of pre-fault. Now during the fault again it is similar to this, and the post-fault, that the fault which has occurred here, sorry, so this fault here you can see this impedance is same, here this line is cleared, so this is a fault clear. So this impedance is just like in the previous case post fault. So just we have here this curve here is basically the fault cleared. At that time fault is clear, but it is not a post fault. Post fault is again here this condition where it's again it follows the same PE. So in this case here your operation is at point A. Again it is an intersection of PM naught and your the PE angle, that is the pre-fault, and this after that there is some fault. Your system is coming here, that is your during the fault condition it will be try to follow here, and then once fault is cleared, there is a clearing angle. Here it will try to go at this point because the now P during the once fault is cleared it is following this. Now till it is oscillating, this line was opened, it follows this. At the same time the circuit breaker tries to close it, means it is suddenly here it is increased here. Before that here it is a decelerating completely, it is your after few cycle it is closed. What is happening now? This is coming here and now again following this, and then it is coming back because this area is now more. So it is more oscillating because we are taking more power here. So now area again for the stable, here this area 1 will be equal to your area 2, and in this case you can see your area of margin here it is very high because line is not ripped. So you can feed more power, so your system is more stable. So the outage of line again creates some criticality of the line. If we said in the previous case it was this area only, now we have this area, so your system is more stable. So outage of line sometimes creates some instability and the system is very clear near to the stability margin. So we want to, this RC is called angle of reclosure, we want to know, and this your this delta D is angle between clearing and the reclosure. This angle we can determine and we can know that it is cleared at this point, and then we can see what should be the critical clearing time in this case. We can again similarly determine. Now again we want to get the what should be the critical clearing time here, delta CR. Having the reclosing facility this angle is given to you, that is a delta D. It is known because it depends upon the circuit breaker configuration. Automatically it reclose, maybe one cycle reclosing, maybe 1.5 or 2 cycle reclosing. Means one cycle it will wait and then it will again reclose. And again the fault is persisting. What will happen? This will open, circuit breaker will be open and it will not reclose again. It is only once. So in this case we want to determine what will be the critical clearing angle, this one, so that knowing this facility in the in our circuit breaker, we want to determine that your fault must be cleared before this angle, otherwise your system become unstable. So in this case your area again using equal area criteria, this area should be equal to your area this now, your area D, E, F, G, H, D. So this is the complete area now we want to know. So area 1 or you can say A1 should be equal to your area A2. Now this area will be equal to nothing but the PM minus your this P2 of integration, that will be equal to from here to here. Now we have the different curves and different area. Now we can divide this area into the two parts. One is here 1, here is another is 2. So 1 is your nothing but is the PE3 because it is the PE3 here. PE3 max minus PE, and it is from delta CR to delta RC, reclosing angle, plus this area. This area is from RC to delta max, PM1 here, minus PM delta. And now you have to solve because this angle you know, you can determine this knowing the PM and PM1 max. You can calculate the delta CR knowing all this value. So here we can get the value, we can substitute this RC CR here and we can get this value delta CR, that is your critical clearing angle, and then we have to design our system based on that one. Now same theory can be extended, can be applied to the two machines case, in which here this two machine having the different inertia constant, here it has a different inertia constant, and then we can add and we can apply together. So in this case we want to apply the equal area criteria for the two machine case is a special case, and these two machine case can be represented by equivalent a single machine connected to infinite bus. Here we have the generator 1 and another is generator 2. This generator 2 is having all the parameter that is denoted by the 2 here suffix. So here it is having M1, it is having D1 damping constant, it is having delta, it is 2, so it will be 2, it is 2. This case it is your M1, it is your D1 and delta 1. So we can write the dynamic equation, that is a single equation, even including the damping. So here the damping term is included. Normally till now we have ignored the damping because this is related with the speed of the system. So this is a M1 delta 1 dot double dot, that is a double differentiation of delta 1 of here, it is delta 1 written, that is feeding power PM1. Here the mechanical power that is coming to this generator is PM1 minus PE. Similarly for generator 2 we can write this M2 delta 2 double dot plus D2 delta 2 dot, that will be equal to your PM2 minus PE2 that is coming from this side. If losses are neglected, what will happen? This, the PE1 plus PE2 in this system, the total PE here that is injecting, that must be balanced. That is a conserved. Energy cannot be going anywhere. So losses are 0 means the energy which is feeding, that will be the balanced out. Means whatever here you are feeding, it must be taken by some machine. So this is PE1 plus PE2 equal to 0. Similarly, the energy, mechanical energy that is coming into the system, the PM1 plus PM2 is also equal to 0. Now substituting equation 3 into 2 here, we want to substitute the equation 3 here. So substitute equation 3 into 2, we'll get here your M2 delta 2 double dot plus D2 here this side, and this we are replacing this, complete these two equations, that is PM2 and P1 in terms of P1, we can write this minus PM1 this, and it will be your plus P1. Assuming the uniform damping, means damping here is the D1 upon M1, that will be equal to D2 upon M2, or you can ignore the damping. If you are also ignoring, that's no problem, then it is very simple. But if your damping is uniform, so D1 upon M1 and D2 upon M2 is equal, then, and also we define the delta 1 minus delta 2, that is a delta 1 2. So we can write a equation M naught delta 1 2 double dot plus delta 2 delta naught delta 1 2 double single dot is equal to PM1 minus P1, and this PM naught will be the basically the parallel combination of these angular momentum, that is M1 and M2. So M naught will be equal to your M1 into M2 divided by M1 plus M2. Similarly, D naught will be D1 into M2 divided by M1 plus M2. So this is your equivalent system, and we can again apply our equal area criteria. Now for the single machine, it is very easy, no doubt, to know whether your system is stable or not. We can analyze and we can calculate your critical clearing time, we can see the stability of the system, and we can only know the relative stability. We want to get the what is the delta variation. It is not a time domain simulation at all. It is only giving information about the stability of the system. Means your system is stable or it is not stable. But that is not only our concern. We want to know what is the system behavior during that period. Means what is the speed deviation, how speed is changing, what is your delta is changing, that is also required. And for that we have to go for solving the differential equations for the different intervals. So this is a numerical solution to the swing equations. We have written the swing equation is this during the pre-fault condition, during the faulted condition this equation, and post fault here, if no line reclosing here we are not considering, means fault is cleared by the outage of line, means this line is stripped after a certain time, and this is the post fault is only this, only one line is existing along with the GTN generator transformer, and this is your this equation. So the equation 1, 2, 3 here can be solved by the numerical methods for solving the nonlinear differential equation. They are the nonlinear differential equation. Why this delta here? This is also delta, this nonlinear function here. This nonlinear. So this differential equation is a nonlinear differential equation of second order because here d2. And that can be solved by the various methods. Methods may be your Euler's method, trapezoidal methods, Runge-Kutta methods. We can show the numerical results of the power angles with respect to time, that is a swing curve. A critical clearing time can be determined by this method. In addition, this method can be applied to analyze a transient stability in a multi-machine system. For the single machine system, as said, equal area criteria can be easily determined, and we can say your system is stable or not stable. We can also assess what is the margin available with you if fault is cleared at particular time, so we can know the relative stability. But we want to know the performance, that is a time domain simulation is required, so we have to solve these three differential equations. Moreover, hold this swing equation here we have modeled as a simple classical approach, and that is not valid. Means we have to go for the detailed modeling of the machine. Here we have ignored, we have made 7 assumptions that can be incorporated, and then there will be several hundreds of machines in a big power system. So all these will be solved for the system. Then we can see the performance, that the delta etc. variation of each individual generator, and then we can say whether a system is stable or not. So in this lecture we have seen the equal area criteria application for the various configuration of various fault, with the reclosing, without reclosing, fault at bus, fault at a line, and then we saw this equal area criteria can give you the relative stability. It will give information whether your system is stable or not. At the same time, it can also give the margin, that is a stability margin that is available in the system, and it is very useful and very fast, no doubt. But only the limitation of this is that we have made several assumptions. Those may not be valid for big power system, and also it is not possible to form the system into the single machine infinite bus equivalent, and then we have to go for the complete and the real time practical system for the simulation, and for that we have to solve these differential equations for all the machines, not only one machine. This is the case of one machine. So we have to go in this infinite bus system. There will be several generators, and we have to include, again, this generator is not a classical generator. Classical generator means it's a generator which we have modeled in the classical form, means we have taken only this generator with some inertia constant. Then we can go by several order of modeling of the synchronous machine. It will equip with your excitation as well. It will be equipped with the governing system. So all dynamical equations will be clubbed together along with algebraic equation, because here the power flow of the different transmission lines, they are not connected with the transmission line generating stations. The different transmission lines here, they will be there. So we have to form this algebraic equation, and then we can solve. Sometimes what we do, all the buses, those are not connected, we try to eliminate. We'll see in the later sections. Here they will be eliminated. Only the generator terminal buses are kept intact, and where there is a fault is occurring, and then we can analyze the system behavior. Means we can see the relative motion of the individual generator with reference to any particular generator, and then we can say whether your system is stable or not stable. So with this, now this lecture 7 is closed. Thank you.